Okay, so as we say in the ZK Monk community, ZKGM, to all of you, thank you for joining today, and thank you for your enthusiasm around ZK. I think it's a very important technology for the future, and I'm really glad that we all have this common interest around it, that we want to advance it. And shape its future and innovation of privacy. And so welcome to the first core session of zkForge Bootcamp. And today we begin sort of the actual practical side of the workshop, and hope you guys are all excited and ready to officially start learning about ZK fundamentals. And so today's session will be an intro into ZK with Laurie Peltonton. Thank you so much for being here and being a mentor. So Laurie is a blockchain developer and researcher with a strong background in EVM and ZK development. He has extensive experience with layer 2 solutions, particularly with Starknet, and has worked with various ZK privacy ecosystems, including Aztec, Mina, and Alio. And he specializes in developing ZK applications. And also he does research around cutting edge ZK technologies and also writes articles on these various topics. So with that being said, I'll open the floor to Laurie, who will give his presentation. And then after he is finished, we could do a round of Q&A for Laurie. All right. So, sorry. Let's go to slideshow.
Yes, great.
Laurie, are
thanks.
You ready? Yeah.
Thanks for sharing the slides. These things happen. So yeah, welcome from my perspective also to the ZK intro session of the bootcamp. You can just click, I think, 4 times. I'm Lauri Peltonen, as you probably heard. I'm a ZK Solidity freelancer, been freelancing for some 2 years now. Started Ethereum some 7-8 years ago, and at some point I found out about this thing called ZK. I was doing some development in some layer 2 ecosystems, and then I found that, okay, they use this kind of ZK thing in the background. Then I got interested in like, well, what is this thing and how does it work? And so I started learning a bit about the mathematical background and how it works and what kind of use cases there are. So then I'm doing developing and educating and teaching ZK as much as I can. Click. So we'll talk about ZK. Basically, what is it? Some very brief intro how it works. Of course, there's a lot of nuances and a lot of differences between different ZK systems, how they work. But let's have a small intro into it. Some use cases, how they work, where they can be used, how you can use ZK even, and then something about how I see the future of ZK, how we will start adopting it, and what is the current situation and how will we progress from here. Click. So as for the history, it started already like 40 years ago. There was a research paper published in '85 that included the word zero knowledge, and that they had this new concept that, oh, let's not reveal any information. And then there was a lot of silence. Nothing happened for basically, I don't know, 30 years. Click. Just click to the end. So 2000, there was still nothing. There was nothing happening. And then 2013, someone actually published the next meaningful research paper about ZK. They actually got it to work, and that was like a weird thing that before that it was all kind of like theoretical, that in theory we can do this kind of thing, and then 30 years later someone actually implements it properly, or actually shows that it's possible to implement it in our lifetime. And then it kind of accelerated from that, and maybe 5 or 10 years ago it started actually being reality that we can actually use ZK. So this is the point where we are currently, that we can actually use ZK, and it's gaining traction. Click. And if we look at the actual term zero knowledge, what it actually means, it's actually it's used in very confusing ways. Many people say, yeah, we have zero knowledge this and zero knowledge that. So whenever you hear this term, just be very cautious what they mean, because strictly speaking, it's not about all the things people usually refer to it. Strictly speaking, it refers to privacy, actually. So it means there's no information leak. If you share something, if it has zero knowledge property, it means there's no information leaked from this data that you share. Or actually, to be a bit more precise, it means there is zero extra knowledge leak. So if you share and there's zero knowledge given to the other person, then what's the point of giving that data? So the point is to hide exactly what you want to hide. The point is not to hide everything, because then the other person doesn't get anything. So you can choose what you share and you can choose what you hide. So this is the zero knowledge property. But as I said, it's used in a very broad way in everywhere around. So in zk, there's these two concepts. Yeah, let's go to the next one. There's these two concepts, a prover and a verifier. These two basically entities who are all the time involved in all zk protocols. Click, and just click until the end. So the prover has a claim they want to make. The claim can be like various things. It can be like, okay, I know a number that has certain properties. Or maybe it can be like, okay, I know I have an algorithm that does certain thing in a certain way. So I have this claim and I want to prove it. So this is what I can use zk for. And then there is this other entity, the verifier. They get a proof from us that, okay, I made this claim. If you go back a bit, I made this claim, and they get this proof, and then they can verify whether my claim is valid. And there's two ways to actually do this. The traditional or the easy way kind of is like there's these two entities, they interact with each other. Like, so prover sends something to a verifier, and the verifier responds, okay, I don't believe you yet, so send me more of something. Then the prover does something more and sends more, and the verifier says, this is a bit better, but I still don't believe you, and maybe give me a little bit more of this and this and this. And this kind of like a back and forth that can happen like many times. But it's really inconvenient to use this kind of zk systems. Like imagine if you are the prover and someone else just wants to be the verifier. You basically have to both be online at the same time. So usually this is not used in an interactive way. So there are ways to make all of these interactive protocols also non-interactive. So what happens in non-interactive protocols, zk protocols? Basically, the prover, as before, they have a claim, they generate a proof for it, but then they get to send it somewhere or even publish it somewhere, and whoever wants to verify, they can take the proof and verify it. So there's no interaction, there's no direct interaction, and once the verifier wants to verify something, they just take the proof and they verify it, and that's it. They don't ask anything more from the prover. So these kind of things are a lot easier to use. Next, please. So the basic flow is you have this claim, and then you have this prover program. The program itself, like either you make it yourself, either you write it yourself, or then you have some developer. Maybe you hire some developer to write the prover program for you. And this program is very specific to your claim. So if you want to claim that I have a number that has certain properties, maybe I want to prove that I know the next prime number or something like that. Then the prover program has all the logic to verify that, okay, or to prove that this kind of claim has been made. And once I run this prover program, it gives out this kind of proof. And the proof is just something you can send to anyone who wants. And anyone who wants to verify, they have this other program called the verifier program. And they just input the proof into the verifier program, and out comes like, is it valid or not? And okay, let's go to the next slide. So some basic properties of zk systems. The proof size, whenever you generate the proofs for something, especially if it's something a bit more complicated than just I have one number. If it's like a lot of data or something, the proof size is basically always a lot smaller than the original claim. So I can have a claim of 1 terabyte of data, and the proof can be like 10 kilobytes. And the part that takes the most resources is the proving part. But whoever has this proof, can verify it very, very easily and fast. So this gives this kind of like very nice scalability properties that just one entity generates a proof. Nobody has to trust that entity. And anyone who wants to verify, they can very easily, very fastly run this kind of verifier and verify the proof. Next. You can click done again. Yeah. So let's go back. As I was saying, the verifier program, it's not generic. It's always tied to the prover program. And what it usually means that there's this, whoever writes the prover program, they usually generate also a verifier program based on this prover program. So these two are tied together. So the verifier is always, it's verifying proofs for one certain prover program. It cannot verify other proofs. So this is the context it has. It knows the context, basically, what the prover is trying to prove. But of course, it doesn't know the inputs to the prover program. So that's usually the private part. And what it basically does, it just says, yes, this is valid or this is invalid. And it doesn't give you any other information. Next, please. So here's an example, like a very simple example of the zk privacy thing. Let's say I have two numbers, A and B. They can be whatever. And I multiply them together and I get a C. Next, you can click to the end also. So these A and B are private, but the C is public. So nobody gets to know what my A and B, but the C I can just publish somewhere, wherever. And what the verifier, if you run this verifier for this kind of prover program, you will find out that whoever generated the proof, they know some A and some B, but they have no idea what those numbers actually are. They know that if the prover has multiplied some A and with some B, they get this public C. But that's all they find out. Of course, you can modify the prover program. Maybe you can maybe you want to make the B public also. That's fine. So then you only keep A private and you publish B, C, and the proof. It depends on your needs. Next, please. So we have this zk kind of like, this is a new thing, and it's a very complicated thing. So why do we actually bother with this? Why do we actually want to use zk? There's a lot of different cryptography already, like research and established like a million years ago. So why not just use what we have, like encryption? Okay, encryption can hide your data. Compression, yes, that can make something small, and commitment schemes that can bind you to some data. But the simple answer is that none of these can provide the same capabilities as zk can. Basically, at least all of these three, they can provide some of the capabilities, but you would have to combine all of them to get the same stuff as zk is offering. If you go forward two more, I think. One more, yeah. So there was this example, A times B and C equals to C. This is something you cannot accomplish with any other cryptography. And zk is the only one who can get other people convinced that I have A and B, secret A and B that results into C. Or that you have 1 terabyte of data and the proof is like 10 kilobytes or whatever. So you could use traditional compression. Yes, you will not get 10 kilobytes, but at least you will get something smaller. But that doesn't prove anything. So it's always lacking some of these properties if you use any other cryptographer. So this is why we basically have zk. Next, please. So I like to divide the zk use cases into three categories. The first is succinctness, which basically just means that you have something big and you want to make it small. And this is especially useful for if you have a lot of data or large computation or something like this. And it's quite handy for computational networks, which basically blockchains are computational networks. So it happens to be quite handy for blockchains. And what is kind of like an extension to this property is the verifiable computation. So you can prove some computation, but you can also verify it. So with this property, you can ask someone else to do the computation for you. And we will see an example of this a little bit later. But I think the most interesting and the coolest aspect of zk is the privacy properties, or the possibilities of privacy. So you can prove that you have some data and it fits certain criteria. For example, like multiplying these numbers results into C. That's the criteria you write, and you don't want to reveal the data. And this kind of stuff can be used for financial stuff. Like you can, like if you're applying for a loan right now, the bank is asking like, okay, how much money you have in your bank account? Well, you send your bank statement and that's it. But with zk privacy, you could only send a proof that my account balance is over €1 million, and that's it. The bank will not find out how much money you have, except that you have more than €1 million, or that you are over 18, like to some website. And the website will not find out how old you are. They will only find out that you are over 18. That's all they need. So it can be used for this kind of general internet privacy. And I think it will be used a lot in the near future. Next, please. So this is related to the succinctness. We will look into this a bit more in the next slides. But basically, the succinctness is very handy for blockchains, for zk rollups and co-processors. Let's go to the next slide to look a bit more into this. But before we actually go to the zk rollups, let's have a look at the layer 2s. But what actually are layer 2 blockchains? So we have kind of like the layer 1 at the right, like that. Those are the, let's say, established blockchains, like Ethereum, Bitcoin, Solana. They have the consensus layer. They decide which transaction comes first, which is invalid transaction, these kind of things. And they have a pretty good security. Like they are very, very well maintained, and they are very secure. This is like, of course, very cool, but because they are so established and so kind of like so secure, they are not efficient in many sense. So often, like projects or someone wants to create a new layer with their own rules. So what layer 2 is basically, it's a layer on top of layer 1. It has different performance, usually a lot better performance. It has different payment models. Maybe you don't want to pay with the same tokens as in the layer 1 or something. You have your own token in the layer 2, for example, whatever. And you can write whatever rules you want. Maybe you can only do transactions on Tuesdays. It's up to you. So if you click a few. So between these two, the layer 2 is sending certain kind of updates to layer 1. Let's not go into the details too much. The next slide, we will have some more info on that. And then there can be like arbitrary messages you can send through bridges. So if you want to send a transaction from layer 2 to layer 1, you can use some bridge, and the other way around also. Then if you go to the next slide, we will actually see a bit more how zk rollups work. So we have our 2 layers, the normal layer, basically. We have layer 1, we have layer 2, and kind of between or around those all, there's this off-chain computation. And if we start from the left, there's the layer 2, it's basically the normal blockchain. There's transactions, users making transactions. The transactions are related to the node client, whatever. The nodes are collecting the transactions and sending them somewhere. And this is the part where we actually don't behave like a normal blockchain anymore. Where we send those transactions is basically an off-chain entity called a sequencer. And what it does, it collects our transactions from the layer 2 and just basically builds a block from those. So every time a block is full, it generates a block and sends it forward. And the next entity is the prover. So the prover is configured, it will get blocks or multiple blocks, or it depends on the configuration. It will get some sort of transaction information, and it will generate a proof for that. Usually it's maybe per one block or maybe per few blocks. So it will generate this kind of normal zk proof that these transactions inside this block, they followed certain network rules. And once it generates this proof, we put this proof inside kind of like a normal transaction. And now we have this transaction which includes our zk proof. Then what happens? We go one step to the right again, and we send this normal transaction to layer 1, where we have this special verifier contract. It's a kind of like normal verifier, which is tied to the prover, which is used in the off-chain. So the verifier knows the context. It knows that we are kind of trying to verify these kind of blocks. And then it says, okay, this is valid, or this is not valid. And once it kind of outputs this kind of information, then all the layer 2 nodes they're monitoring this verifier contract. Okay, now it output a new information for this one proof block. And once these nodes in the layer 2, they find out, okay, this proof for this block is valid. So let's finalize all the transactions in that block. And then all the transactions in layer 2, those are finalized. There are many variations of this, but this is basically the general flow how zk rollups work. Yeah, let's go forward. Now this is related to the succinctness also. So it doesn't have to be about blockchains. It can be just whatever internet data you have. But the whole idea is that you have a lot of data. You don't wanna send it, maybe because of privacy reasons, but it can be just too much. Maybe there's no storage capability. So you generate the proof that I have 1 terabyte of data that follows certain rules, and you just send this proof. Maybe it's like 100 bytes, whatever. The whole idea of succinctness is that you have something big and you make it small. It's kind of like that simple. And if we look at the next use case, the verifiable computation, this is a bit more abstract and not very much used currently. There are many ways to do this currently, but I think it's not very widely used yet. So let's say you have a normal cloud computing platform, whatever, doing some computations, and you have some big computation you want to do, but you're like, nah, I don't want to do it myself, so let's send it to the cloud. And then the cloud gives you a result, and then you're like, okay, I get the result, but how do I know if it's valid? So what zk gives us, we can actually use a prover in the cloud also. That it's actually a service inside the cloud that while it's doing the calculation for my data that I gave it, it's also generating a zk proof for the calculation. So once what it gives us, the cloud gives us all the proof that the calculation is valid, and also the result. And when I get the result, I can just, okay, now I have the result, but is it valid? Then I can just check the proof. I can use the verifier program and check if the calculation has been done correctly. Oh, okay, it verifies correctly. So it means that the cloud provider did their calculations as I wanted them to do. We can just go to the next slide. Let me have some water. Oh, actually, if you can go one back. Sorry. Yeah, so what I wanted to mention about this is it's shifting the trust assumptions. So nowadays, if you want your cloud provider to calculate something, you have to trust it that they give you the right result. But with this kind of zk, if you get the zk proof for the computation as well, you no longer need to trust your cloud provider at all. They cannot give you a zk proof that successfully verifies if the computation has been done in different way. So the only way they can give you a valid zk proof is if they do the computation as you told them to do. So in theory, you can start using any random shitty cloud provider or somebody else's laptop to do any computation you want, and there's no way they can cheat on it. Yeah, let's go forward now. But yeah, I think the most important or interesting use case is the privacy. So the basic idea, you just don't send your sensitive information. It can be your medical data, by your bank account balance, whatever. In the blockchain, context, it's usually like maybe you have some transactions you want to hide, maybe you're doing some trading you want to hide, maybe you have some voting, you don't want everyone to see how you voted in certain things. And then if you go outside blockchain and gaming, for example, you can get rid of centralized servers. You can send all the data to all the other parties who are playing the same game, and they can just calculate, they can just verify certain things and do their things, but they don't find out your original data. So they get this kind of like partial information. You can use it like fog of war, like you only see some part of the map and so on. And in theory, if we had like very good zk privacy all around it in the internet, we wouldn't get this kind of data leaks because nobody would have our data. So let's look at there's like a United Health is leaking all the data they had accidentally. In theory, if we only send them zk proofs of our data, and they have nothing to leak. They can maybe store our zk proofs, but those only give them exactly the data I want them to get and nothing more. So we would, in theory, get rid of all the data leaks like this. That's of course a bit like not tomorrow that's going to happen, but it might happen in a few years. Let's go forward. And some notes on the privacy. Yes, the zk privacy is awesome. But as I was kind of hinting earlier, like whenever someone says about we have a zero knowledge protocol, most likely it's not actually a zero knowledge protocol. They use the same technology, but they don't provide any privacy. I would claim that 95% of all the zk protocols, they don't care about privacy. Maybe it's not a priority for them, or they chose not to implement privacy because it makes things some things like a bit like inefficient. So, and the reason why they don't do privacy or don't have privacy, it's because of us, because of all of us users, because we don't care about privacy. Like let's say that you are going to your Instagram account. Okay, it's your connection is secure. Nobody can read your data. That's awesome. But Instagram gets all your data. You don't care. You're kind of used to selling your soul to this kind of like huge platforms because everyone does it. But if you kind of cared enough and if you were ready to pay for the privacy, then those platforms would also add more privacy. But most of the privacy projects I've seen, they really struggle to find users because the users really don't want to pay for the extra privacy. And the cost doesn't have to be like money. It can be something like it's just inconvenient to use. So that's all about us. If we go forward. Some notes about the proofs, who generates it. And that also depends on the privacy needs and the privacy requirements. If you don't care about the privacy, just anyone can generate the proof. You can send all your data, you can publish in the internet and ask someone to generate a proof for it. That's fine. There are different services, different markets for that. But if you have some private data, well, you probably don't want to send it from your local machine, probably anywhere. So you have to trust the entity that generates the proof. So either it's your own device, or maybe there's some trusted server somewhere that you okay, let me send my data there, and I trust the server enough. So it really depends on, do you need privacy and what kind of privacy you need. Next, please. Yeah, if we just very quick look at the mathematics, let's just say it's complicated, but the whole point is that you don't need to learn the mathematics. If you want, it's a lot of effort. But if you want, you can do it. But I would say it's not worth it. So just do your own thing, do your development, do your business things, but forget about the mathematics under the zk. And we can go to the next slide. The learning path, how it usually works, is that you start from this kind of use case. Oh, there's zk in enables this kind of stuff. And that's really cool. And if you're a developer, then you start building something on zk. Like, okay, that's a bit harder, but it's very much doable. And then if you're a bit weird, you start learning even the mathematics and the theory. But as I said, like if you get that far, that's like awesome, but just don't bother usually. And especially in this course and all these kind of lectures, we focus on the two first. So that in this lecture, we have a look at the use cases development side also. Next, please. So how you can start, or from the development point of view. So basically, if you start from the use cases, you start thinking of like business needs and where can these kind of things be used. And at some point, you need someone to develop this thing. Or if you're a developer, you can start from the kind of like the other approach. You can take some languages, some zk languages, and there will be a next lecture about all these zk languages. Or you can choose a different ecosystem. Like there's different zk ecosystems, different zk systems, and you can mix and match. You can decide how you want to do it. Next, please. Something about the adoption. If you click a few times. I hope the privacy will be the main thing that will go forward. We already use a lot of the zk in blockchains, but how will we get zk to kind of go to mainstream? I think this is, in my opinion, this is a bit similar to like 100 whatever years ago, when people started getting cars and they were using horses. People like, nah, we don't like. Why would I ever want a car? Like I have a horse and it works. But then at some point, like someone, their neighbor maybe gets a car. Oh, this car is nice, it goes. But then you're still like, nah, like what's the point? This works what I have. My horse is fine. But at some point, you start realizing that everyone else is using a car and they work fine and they are much better in many aspects. And at some point, you're nah, like what's the point? This works what I have. My horse is fine. But at some point, you start realizing that everyone else is using a car and they work fine and they are much better in many aspects. And at some point, you're like, okay, maybe I should switch also. So at some point, people will realize, okay, we have these options. We now have a car we can use. So let's switch to this better thing. But first, we have to create all these better zk implementations and projects. And that's something everyone is currently working on. Next, please. So for the future, the technology is getting better. We are still super early. The technology is getting faster all the time. All the time, people are researching new weird stuff. The usage is gaining traction. It's especially very much used in blockchains. I hope the privacy will be the main thing that will go forward, but we'll see. And the further we get, the less we have to care about the mathematics. So currently, if you start developing something, you will see some of the mathematics and you will have to understand some of it, a little bit of it. But the further we get, the less you have to care about that part. And that's a really good thing. But basically, whatever you think, we are still early. Next, please. So to conclude, zk is super cool. It has 3 main use cases that we were going through. And it enables some stuff that just simply isn't possible with the other more traditional cryptography. It kind of combines many features from other traditional cryptography methods, but nothing else can do the same things as zk can. Okay, at least nothing traditional. There are some new weird other cryptography stuff, like fully homomorphic encryption, but let's not go there. But the main point is, like, if you're here, you are still early. And this is the perfect time to jump into the train. So welcome. Click, please. Yes, that's all I have. So here's some cookies for you. I was seeing some notification that's like there's a million questions, but I have no idea how we should go through those.
Yeah, so we have still some minutes, some time left for questions. So I guess if folks could raise their hands, that would be probably the best way to proceed. And I'll try to go in order as best as I can. Okay, so thank you, first of all, Laurie, for the presentation. It was a really great introduction. Okay, let's have Judith Yadav. Judith, do you have a question for Laurie?
Yeah, so as you mentioned that approver is linked with verifier or verifier is linked with approver, then how could I believe a verifier is implemented appropriately to put it in context with the particular approver?
That's a really good question. So basically we have prover and verifier, but how do we know that they are actually doing how do we know that verifier is doing what some people claim that it's doing? Maybe it just always says, yes, this is valid, no matter what you input it. There are various approaches to this. The most traditional approach or the kind of the easiest approach to this is that you put your verifier on chain, you write it as a smart contract. So once it's on chain, it's immutable. And when people start using it, basically slowly gains kind of like trust, like social consensus agrees that this is a valid verifier. Or maybe you can audit the verifier, but that's a really horrible work and really costly. Or something else. Maybe there's some sort of trust relationship between these. Maybe you just explicitly trust the prover to give you the verifier you think they give. So it depends, but that's a very good question.
Okay, thanks for that. And Kaushal, do you want to ask your question? Yeah, Kaushal, do you want to go ahead and ask your question? All right. I haven't heard from you, so I'm moving on to Ashwin. Ashwin?
Yeah. So just sort of an extension of all the privacy-based applications and adoption techniques. I actually think that it's the thing that drew me in as a lawyer to this place. And I mean, just sort of intuitively, it's like you can build bridges across so many businesses that would otherwise not do business because they don't want to take the risk of sharing data, right? But do you have sort of a framework on what you think, which kind of business is more likely to adopt first as opposed to later? And to make my point a little bit more concrete, I think I'll give two examples. So one is, of course, when you're listing stocks, and I'm ignoring blockchains for now to focus on the real world. So if you're listing stocks on a separate country, you often have to make the same disclosures all over again to get it listed there. Do you think something like a zk proof would speed up the process and therefore improve efficiency for everyone, or would it be more like would you start at a retail level before you even go talk to a government, or like how do you think about these things in general?
Like in theory, that sounds like very much something zk can do, but in reality, I think the problems will be related to different countries and different legislations. So even if I have a prover, even if I write a prover that proves that all the properties of a new stock or whatever, even if all the properties are valid and this should be a valid stock, then probably the rules are totally different in your next state or next country. So it's very difficult. It's basically impossible to write a program that suits everyone in that kind of way.
Right.
Right, folks, we have around 13 minutes until the end of the session. So let's try to get through them a bit quicker. More, Goye? More, do you want to ask your question? All right, moving on to Mattia.
Hello, can you hear me?
Yes, now we can hear you.
Yeah. I was asking, whether it is suitable for in real world use cases, or use cases different from rollups, right? That are commercially viable.
Sorry, so what's the question? Or like what kind of use cases are commercially viable, you mean? Or
Meaning usually the more mainstream use cases of zk as I know it now are the rollups, right? Are there any maybe kind of Web2 use cases that are commercially viable? Maybe the verification might be kind of expensive, if I can say so. Are there actually real use cases that can be cheap? For example, if,
you're breaking up a little bit, but if I understood correctly, like other in outside blockchains, what are the use cases or that might be commercially viable? I would say that privacy, I hope, will be commercially viable. Currently, it's challenging, but once we get enough of privacy options, then hopefully that will become viable. And the verifiable computation is another one that will possibly take off in different forms that probably I cannot or nobody can predict yet. But the easiest way form is just like give your hard computation to someone else to do.
Great, thanks.
Okay, we have to go a bit faster with the questions to make sure that everybody sort of has a chance to ask. Mattia? Yeah, Mattia, go for it.
So and if you don't manage to ask your, oh, sorry, just go ahead.
Yeah, so I just have one more question. I have been building around privacy, and I think like in the slide there was one point which was much more interesting, like why not use cryptographic algorithms? So if you could dive more deeper into it, like let's say there is FHA and all the stuff as well happening. Why so much focus on like zk proofs or something?
Yeah, there are other stuff that provides similar properties. zk it provides certain properties, and other cryptographic means provide other properties or like somewhat overlapping. But there's nothing that provides exactly these same properties. That doesn't mean that zk is the best. It only means that zk is the best for very specific use cases, and for other use cases, there's probably something else. So this is not like a silver bullet. So this is just one more tool in your cryptographic tool belt that you can use. And you have to basically know where to use zk. Just don't put it everywhere.
So can you just classify like self-sovereign identity? Where does it fall? Like, will it be? I see products like Hyperledger ND which use cryptographic signature, whereas products like Privado ID that use Circom zk circuits. So how do we differentiate? Like, do SSI require zk or?
I think zk is mostly used for privacy aspects in those personal data things. So you can use encryption, but it depends on your needs. It really depends how the protocol is designed.
Okay, good.
And what I was saying that if you don't have chance to ask your questions here, just you can free to poke me anywhere. Just my chats are very open, so just in Telegram or wherever.
Yeah, guys, if you could also please add your questions to the chat, we can get through them faster. That would also really help to make sure as much people get to ask their question. Philippe, do you want to go ahead?
Can you hear me?
Yes.
Yeah.
I wanted to ask maybe the chances of a collision happening, or maybe a zk hitting, if it's supposed to maybe be binary, instead of hitting a 1, ends up hitting 0. What are the chances?
Kind of collision things, those go into the cryptography side. There are security parameters. Basically, you can decide how kind of secure your zk protocol should be. There are certain like standards, but if you kind of, so for some reason, if you are okay with very low security parameters, then you might have some hash collisions and this kind of things. But in normal zk protocols, it's secure enough that you don't have to worry about these kind of things.
So it can be totally eliminated and become zero collisions.
Not zero. It's never zero. It's all about probabilities, but close enough to zero.
Thank you.
I guess I am the next one. Lori, thank you for the great presentation. I have a question from the ID perspective, but I think I got your opinion in general. But so we do rely on a third party to verify that that's my identity, really. Like we have projects like zkPass, and I can generate zero knowledge proofs proving that I'm older than 18. That's good. And the data is private to me. Yes, I can do it on my device. But in the first place, that data was verified by a KYC entity, for example. So how do we securely transfer that data, and how we are ensuring that that's not leaked on the other end? I mean, that kind of really confuses me. Yes, the proof generation, correct. It is totally private, and I'm selectively accept to reveal my information or not. But the verifying the trusted entity, the government itself, for example, the issuing entity of the identity itself, could be a point where we get the data leaked. What do you think about this one? Thank you again.
That's a very difficult nut to crack. I had no answer to this. Like, how could we prevent the government data from leaking from the government itself? Or how can we verify that the government uses the right data in the right way? In theory, zk can be used there, but I would imagine it's a hellish process to get that done.
Okay, I think I'm the next. Hi, Laurie. So wanted to ask about as you mentioned about there are verifier and like prover as well. So let's say the small scale business or medium scale business. So do you find that it is like not cost effective solution compared to what we have traditional encryption patterns? Because let's say I'm just a small scale company, I just want to provide identity as a management service, and where I'm just going to use resource as a zk verifier thing and everything. So in that case, it's really, you can say that not that much cost effective. So is there any another way to like make it cost effective, or it is as it is that we need to keep it?
Of course, there are many zk protocols that have different kind of properties. Some are faster here, some have like bigger proofs, some have smaller proofs, and so on. You can choose from these. That's one way to go. But I think the biggest challenge is the architecture, that you need this kind of like prover and verifier thing. Like, who is generating the proofs, and who is verifying, and how can you trust the verifier program, and all this kind of stuff you have to decide when you figure out the architecture. So I wouldn't worry too much about the cost per se. It's more about finding out if zk is the right tool for your project.
Okay, but addition to that, let's say like it is using the resource, like it is resource intensive task. So in that case, like it will add up the cost down the line, to be honest, for any business case. So that's why it is like having the adoption issue, or
No.
do you find it different? Okay.
Yeah, well, that's of course like maybe small part of the issue, but I think it's a bit complicated to use because we have the prover and verify and this kind of architecture. The technology is new, so people don't yet know how to use it. There are no good, like, we have some templates, but we need a lot more like template project that, okay, let's use this, and this already provides what we need. So there's just real work that needs to be done to gain adoption.
All right, thank you. Really appreciate it, man.
Yeah, so we have time for like one more question, and then the rest of the questions can go on our Discord, and we can also help answer your questions. Yeah, sorry, unfortunately, we are almost at the peak of the hour. So let's have Zhao Mao.
Yeah, that's me. My question is on, you said that zk gives us privacy, but then what about auditability? Because maybe most people or auditors, they want to audit the maybe transactions or what has been happening. So do we need like selective disclosure, or maybe viewing key patterns like we have in Zcash? so that maybe users can privately operate maybe their day-to-day, but reveal to auditors when needed.
Yeah, that's one possibility that you have to decide when you're figuring out your zk architecture. So do you want to give access to some external party to some of the transactions, maybe all of the transactions? And how some of the ecosystems do this kind of things is they add this kind of property that are called a viewing key, which gives whoever has this viewing key can view all the contents, but they cannot do anything else. And maybe it applies for only one transaction, or maybe it applies for all the transactions from one sender, or maybe it applies for everything. That depends. So it depends. Of course, that also depends what you need.
Okay, I think we'll end it here for now, but do come to our Discord channel. We have study groups where we can continue the conversation, explore any points that you wanted to expand on, which we didn't have time for here. And yeah, thank you so much, Lori, for giving your presentation and introduction to zk. And personally, I'm really glad to know that we are early. That's very promising, means that we're doing something right, being here, running this bootcamp for everyone to learn. So yay, go zk Monk. And